In this video, we are going to discuss how to calculate the center of mass for a system of objects. The question says, find the center of mass of the arrangement of uniform identical cubes shown in the figure. The length of the side of each cube is d. Now, whenever they say identical means the objects have the same dimension. Each of the cube will have the same side d as well as they have the same mass. If you want to find center of mass of the arrangement, we first need to know what is the position of center of mass for each of the cube. Now cubes are symmetrical objects and here they have uniform mass density. So whenever you have an object that is symmetrical and has uniform mass density, like a square, a sphere, a circle, or a cube, for such objects, the center of mass lies at the geometric center. So for each of these objects, their center of mass will lie at the geometric center. So I can show the position of center of mass for each cube at their geometric center like this. I need to find what are the position of these center of mass for each of the cube, and then I can use that position values to calculate the center of mass of the entire system. So let this be cube 1, this will be cube 2, this is 3, and this is cube 4. So I'm going to find what is the position of center of mass for each of the cube and then use those coordinate in our rule to find center of mass of the system. Let's start with cube 1. Now if you have an object that is placed at origin, like how cube 1 is placed here, let me draw the coordinate axis is 0 and I have an object, a symmetrical object with uniform mass distribution placed at the origin. Let L be the length of the object. So we start from 0. This will be the length L. And let height be h. We know for a symmetrical object, the center of mass lies at the center, the geometrical center. So if I were to find the position of this center of mass, I know it lies at the center. So its x value will be the midpoint over here, the central point over here, which is L by 2. Same goes for the y value. When I have to find the y value, I have to locate the midpoint, which will be h by 2. So for cube 1, the position of center of mass along each of the three axes, x, y, and z. We will call this axis up here as z-axis. So for cube 1, the position of center of mass along each of the three axes, x, y, and z, is going to be d by 2. I can write for cube 1 the position of center of mass to be r1, and along x-axis it will be d by 2, y will be d by 2, and z will also be d by 2. We can call them x1, y1, and z1. Now let's look at cube 2. Cube 2 is placed on top of cube 1. So it is displaced along the z-axis. Along x and y-axis, it is still starting from 0, but it is displaced along the z-axis because it is placed on top of cube 1. So if I were to find the coordinate of center of mass for cube 2, the x and y coordinate will still be the same. I can write r2. X and y coordinate will still be at the midpoint, which is going to be d by 2 and d by 2. But since it is displaced along the z-axis, I need to do some more calculation to find position of center of mass along that axis. Let's try to sketch the situation along z-axis for cube 2. I have the coordinate systems like this, and then we draw cube 1 first. This is cube 1 and it has a side d. On top of cube 1, we will draw cube 2. Cube 2 also has this side as d. Now I know within cube 2, the center of mass lies at the geometric center. And within cube 2, this distance of center of mass, this height, will be d by 2 within cube 2. But when I'm finding position of center of mass from the origin, I need to find from 0 over here till this total height. I need to find what is this total height. So this total height will be d by 2 plus the side d at the bottom. Height of cube 1 plus d by 2 within cube 2. The position of center of mass along z-axis for cube 2 will be d plus d by 2. That gives me 3d by 2. Anytime an object is displaced on any one of the axes, x-axis, y-axis, or z-axis, by one cube, like it is placed on top of one cube, placed after one cube, or placed in front of only one cube, the coordinate of the center of mass along that axis will be d plus d by 2, which is 3d by 2. So here, along z-axis, I will write the position of center of mass to be 3d by 2. And we call this x2, y2, z2. Same thing for cube 3. Cube 3 is displaced along x-axis. Again, it is placed in front of only one box, which is box 1. Within cube 3, we know the position of center of mass along x-axis will be at d by 2 within cube 3. And if I were to find this position from 0, it has to be d plus d by 2, just like how we showed here. So d plus d by 2 is 3d by 2. It is not displaced along y and z axis, so their values remain the same, d by 2 and d by 2, which we can call as x3, y3, and z3. We do the same thing with R4. Cube 4 is displaced along the y-axis, so we will only change the y value. X and z value will remain the same, 3d by 2 and d by 2. So these are the coordinates of center of mass for each of the cube. Now I'm going to use them to find the position of center of mass for the whole system. To find the position of center of mass of the whole system, we will find its position along each of the axes, x-axis, y-axis, and z-axis separately. So along x-axis, I can write the position as xcm for center of mass to be x1m plus x2m plus x3m plus x4m over m plus m plus n plus m for 4 boxes. Generally, the rule is x1m1 plus x2m2 plus x3m3 plus x4m4. But since the cubes are identical, they all have the same mass m. So I can write my m1 equals m2 equals m3 equals m4, all of them to be equal to m. Now let's take m common. I can write x1 plus x2 plus x3 plus x4 divided by 4m.
Cancel the m here.
You are left with xcm equals x1 plus x2 plus x3 plus x4 divided by 4. So this is how you can reduce the equation for position of center of mass whenever you have a system of objects that have the same
Mass.
If they have the same mass, you can take the mass common and cancel it off. And your equation reduces to adding all the position values dividing by the total number of objects. So if I have 4 objects like here, 4 cubes, I add position, the x coordinates for all the 4 cubes divided by 4. Now let's substitute. X1 is d by 2, x2 is d by 2, x3 is 3d by 2, And x4 is also d by 2, divide by 4. So when you solve this, since they all have the same denominator, I can just add them, add the numerator. D plus D is 2D, plus 3 is 5D, plus 1D is 6D by 2, divide by 4. So 3D by 4. This is the x coordinate of my center of mass. We can do the same thing to find the y coordinate. So for y coordinate, I'm just going to use the simplified version of the rule that I found for x. We don't need to resolve everything again. I can just write YCM to be equal to y1 plus y2 plus y3 plus y4 divided by 4. And then we substitute y1 is d by 2 plus y2 is d by 2, y3 also same, y4 is 3d by 2 divided by 4. Again, when you solve them, d by 2 plus d by 2 will give me 2d plus 3d plus 3d by 2 will give me 6d by 2 over 4, which is 3d by 4. And then we find the z coordinate. The z coordinate, again the same thing. I'm just going to use the simplified rule. Z1 plus Z2 plus Z3 plus Z4 divided by 4. So d by 2 plus 3d by 2 plus d by 2 plus d by 2 divided by 4. Now if you notice, these two expressions are the same. They are just written in a different order. So my answer for z coordinate will also be the same, 3d by 4. So I can write the position of center of mass for the entire system R is 3d by 4, 3d by 4, and 3d by 4. This is your final answer. So the only thing to remember is you can use the simplified version of the rule only when the masses are equal. If each of the box or each of the object have the same mass. If the masses are not equal, then you have to use the main rule for position of center of mass, which is x1 m1 plus x2 m2 plus x3 m3 divided by sum of all the masses m. So I can only cancel off the m if they are equal. If they are not equal, I have to just multiply each of the position value with their masses divided by the total mass.